So good morning. I have 11:10, so welcome. Let me get going with the sharing the screen here. So today, what we're hoping to get, we're getting into chapter 3. So this is about force, representing forces with vectors, so drawing these force diagrams, and relating force to motion. And there's Calvin from Calvin and Hobbes. He looks at a balloon. Let's go. You'd think, as most things, when you let them go, they go down. But if you take a balloon and let it go, it goes up. So he has decided that gravity is arbitrary. So the real reason a balloon goes up is because of buoyancy force. So that's not arbitrary. Let me get my chat windows set up here so I can see what's going on. There's been a few questions that people have been posing. Quite a few questions about the Mastering Physics Homework 1 if you're trying to reattempt it. I have a little button which says that I can click on it to allow reattempts, and I keep clicking on it, and I think it's working, but I mean, it looks like it's working from my end, but I don't think it actually is, because I haven't heard of any student who's been able to actually reattempt it, which is terrible. So I'm going to have to think of some other way, like make a whole another assignment that's identical or something like that. So apologize for that. Maybe it, there's some way, I don't know how to do it, but and then I want to see panelists as well in case people have their hands raised. Where's it? Attendees. Okay. Let me go through a couple slides before I go to the hands. Okay, so there's this midterm assessment, which is coming up on Tuesday, September 29th from 8:10 to, well, it's a half hour. It's sort of weird. It's a 30-minute quiz, but the window of opportunity in which you can do it is 35 minutes. So if you start it up to 5 minutes late, you'll still get your full 30 minutes. But if you start it on time, then it ends at 8:40. It's based on chapters 1, 2, and 3 of Atkina, plus the material from your first practical. The format of this midterm assessment is just going to be 10 multiple choice questions, just to sort of make it easier to mark. Right now your TAs are quite busy with the practical stuff. I'm hoping I can get some budget for future midterm assessments that might have a written or a short answer component, and that actually gets marked by a human TA, but just not this one. And I'm trying to work on that. So it means there won't be partial credit and stuff. The quiz is open book, meaning that you are allowed to have aids like your calculator, your phone, I guess, if you want to have your calculator on your phone, course notes, videos, Google searches for static web pages, etc. What I would like you not to do, though, is communicate with the other students in the course or get help from anybody else. No group work or chats with other students are allowed during the assessment. You should try to just focus. The quiz will end either 30 minutes after you start or at 8:45 p.m., whichever comes first. You will only see one question at a time. You have to submit your answer by clicking next in order to see the next question. And you will not have the ability to go back and change any answer after you've done that next. And after completing all 10 questions, you click on submit quiz and you get before the time ends and you're done. There are 3 conceptual questions and 7 questions in which there's some numbers, and some of them are estimating, but there'll be some calculations for most of the questions. I'll also note that about 55 students have gone on and registered for the alternate sitting, which is 2 hours later. It starts at 10:10. If you have a conflict or anything like that, there shouldn't be any problem with registering for the alternate sitting. However, April is going to wait. I just spoke to her. She's actually in today. I just spoke to her. She said that she's going to wait until the form closes tomorrow at 2 before she sends out any emails to confirm that you're going to get, that you are registered. But so for now, if you've completed the form, just assume that you're registered for the alternate sitting. It should be fine. Now let me see if I got anything. So Hyamen, whoop, you had your hand up. It's been up for a while. Did you have a question?
Hello.
Hi.
Okay. So I forgot. I think I forgot the question after you
That's okay.
muted. I'm sorry.
No problem. What about arpit? Question?
Hello, can you
Hi.
hear me?
Yes, I can.
Yeah. Hi, Professor. I was going through the pre-lecture videos on mastering physics, and there was a video of a kart having a fan, and then the person who's demonstrating puts a sail in front of it, and the kart does not move. But there are a lot of videos on YouTube, also done by Mythbusters and other people, which shows that the kart moves on the direction of the sail when the fan is switched on. So like it's really confusing what was shown in the demonstration and what is there on
We
the
could
video.
try it. I think that's it. So that's an interesting thing. If you've got a cart with just a fan on it, you just turn on the fan, then the fan will blow air in one direction and it'll push the cart along, accelerate the cart. And we can show that today. We showed it before. But what if you put the fan on one side blowing towards a sail, so it sort of creates its own wind? Then you've got this idea that maybe it would push itself forward, but it's the fan which is blowing air in this way, so maybe it would go this way. I don't know exactly what would happen. My guess is that it would actually go backwards, and that the fan would, some of the air would go around the sail, and the net sort of external force would push it the opposite direction of where it's trying to sail. But we're going to get more into that today. I'm glad that you're looking ahead at these videos, but I'm going to try to get into that once we get into chapter 3 stuff today. So excellent points here. Looking at the question. As for the chapter 2 quiz that was on the Quarkus, people were not able to see their grades. I think that's fixed now. There's a setting, again, that I clicked on, which should allow you to see the grades for that. So, but I only found it this morning, so give a try again with that. And yeah, you might want to redo question 10 if you did it early. On Monday morning, I think I changed question 10 because there was a typo in that. Okay, hopefully that is helping. Seeing a lot of repeated questions. So I'm going to go on to some material. All right, dynamics. So in physics, kinematics is the study of how things move, and dynamics is the study of why things move. So we're now moving on to the kind of the more interesting thing. And here's a thought experiment, which is James Bond is standing still in the middle of an ice-covered lake. If the surface were, and the bottoms of his shoes and everything were just infinitely slippery, maybe he was standing on little ball bearings or something like that, would he be able to like run away? And the answer is no. He would not be able to, he could jump up and down, I guess, but he couldn't run to the left or run to the right, because it's actually that friction from the surface on the bottom of his shoes, which is going to actually propel him around. So there's this idea in physics, well, you could throw him a rope, I guess. Someone could tie a rope around him. You need some sort of external force. So an external force, unbalanced force is needed to accelerate an object, like James Bond. There's no external force from something else pulling you or pushing you, you're not going to move, you're not going to accelerate. So it's important to define system, environment, and external interactions. So a system is the object or group of objects that we choose to analyze. And often what you do, you see this in the textbook all the time, is you draw a little dashed line, around the thing of interest that you're analyzing. So that would be the system. So let's call him there's the system. Who's that guy? And then everything outside that system is called the environment. And it consists of objects that might interact with the system, touch, push, or pull it, and it affects its motion through external interactions. So some external interactions that are happening here is you've got the surface of the lake. The lake pushes up on the system, which is interesting. You've also got Earth, I guess down here somewhere is Earth. Earth provides gravity, pulls down on the system via gravity. And then you might have some horizontal forces as well. Maybe you've got this person who's kind of anchored on the land with a rope and then pulling this way. But all these things are like the environment. The environment of the system that can have external interactions which end up accelerating the system. Okay. So, and these external interactions come in the form of forces. So what is a force? A force is a physical quantity that characterizes how hard and in what direction an external object pushes or pulls on the system. We say that an external object exerts a force on the system. So from the system's perspective, it has a force exerted on it. So maybe here is this javelin and the javelin toss. The athlete is providing a force on that system. Or there's this guy getting punched. There's a force, an external force pushing that guy's face that way. A force can be a contact force, like you're seeing here, or it could be a long-range force, like gravity. You know, even if there's nothing touching the angry bird, gravity sort of reaches out over a distance and pulls it down over a long range. There's an SI unit for force so that you can measure it and put a number. It's called the Newton, abbreviated N. N for Newton is not a fundamental unit. It can be broken down into fundamental units as such. 1 Newton is equal to 1 kilogram times meters and then per second squared. So it's a little kilograms times meters times seconds to the -2. I want to get up to a poll before we go break here. Okay. So if you're going to draw a force vector, the way you do it, you draw the object, and then you put the tail of the force vector on the object, and then you draw the force vector as an arrow pointing in the proper direction, and with a length that's proportional to the size of the force. So bigger force, kind of draw a longer arrow, I guess, and then you label the force. So we could do this for the James Bond here. If you draw a force diagram, it represents the forces that objects in a system's environment exert on it. We represent the system by a dot. So I'm going to take a black thing here and just say that is the system. And I can actually remind us of what it is by saying it's this guy. He's the system. System equals bond, for example. And then the arrows represent the forces. So what you have to do is kind of try to think of all the forces that could be on him. So we've got the force of the ice on bond. I'm going to call everybody bond B. We've got the downward force, force of Earth on B. This is, and we should put little arrows on here to indicate that they're vectors. And this one is gravity, pulling them down. So those two kind of cancel out because they, he's not falling down, right? And then you've got this force, this tension from the rope. So there's this, and this will be the unbalanced force, the force of rope on bond. And so when you're constructing a force diagram, first you kind of sketch the situation and put a little dashed line around what you want to be the system. In this case, the system is a rock. So here's a rock that's sinking into sand. And then you think about what the external interactions are. Well, the sand is holding the rock up and you've got gravity pulling it down, Earth pulling it down. So then to draw a force diagram, you put a dot near the sketch representing the system, and then draw force arrows to represent all the external interactions. And since the thing is slowing down, I guess, as the rock hits, here we've got the force of the surface being greater than the force of gravity. So that it slows down as it goes down. And just some things to remember at the bottom. Remember that on a force diagram, you only draw forces exerted on the system. You don't draw like the force that the system exerts on its environment. So you might think that as this rock pushes down in the sand, that would be a downward force. And you're right, the rock does exert a downward force on the sand as it's hitting the sand, but that's on the sand. So you don't draw it in this free body or in this force diagram. You only draw the forces on the rock. And so in that case, the sand is pushing up on the rock. Okay, so here's a pull. You toss a ball straight up in the air. Immediately after you let go of it, what forces are acting on the ball? So they're numbered. 1, the downward force of gravity from the earth. 2, an upward throwing force from your hand. And 3, a small downward drag force from air resistance. So there might be some combinations of those as well. So let's put pull. Turn on the lights. We can cancel that. Worked. Wow, this is neck and neck here. I really wish we could all have a discussion here. Let's end the polling. So I'll give you 5 seconds. 2, 3, 4, 5. And polling, share results. So this is a really split thing. So it's either 1, 2, and 3 or 1 and 3. So this is the point, is that if we were in Convocation Hall where I normally teach this, I would ask you all to kind of pair up and try to convince each other. Some of you voted A, some of you voted B. You know, try to convince your neighbors. So what I'm hoping to do once you're all familiar with your practicals teams is maybe you can open up your practicals teams during lectures. But anyway, we can't do that today. I will just tell you what I think my answer is. So I'm thinking that immediately after you let go of the ball, as soon as there's a space between your hand and the ball, there's no more force from your hand on the ball. I don't have a ball. I have an Angry Bird. My tennis ball is somewhere else. So I'm going to throw it up. So it's going up. So why is it going up if I'm not touching it? I think it's going up because it just has that initial velocity. It sort of has its own momentum which carries it up. So the answer I'm looking for here was B. There is going to be, if it's going up, there will be a small downward drag force. That's definitely true. But that force from your hand, this stops acting on the ball the moment you release it. We're going to learn more about inertia as time goes on, but things that are in motion tend to want to continue in motion from their own inertia. And it actually requires some external force to slow them down. So that the reason that the the ball keeps going up is not from your force, it's from its own inertia, you release. Okay, excellent. And then as far as what's going on the screen up here, I did mute the group chat, unfortunately, so I can see everything you're typing in the chat window, but not the other students can. But again, it goes by kind of fast. There, I can see hundreds of things going in the chat here. So I can review it after, but I can't really deal with it during the class. Let's see what are some questions. Why is the force of the surface on the rock greater than the force of gravity acting on it? Yeah, so in that previous slide, Navid's got a good question, which is, why is the force of the surface on the rock greater than the force of gravity? I think that's because it's accelerating. It's actually decelerating. So there's an unbalanced force at the moment that the rock is sinking. So it's about to stop. It's a little bit like, I think there was a quiz question about this where there was a guy on the trampoline, and the question was, at the bottom of the trampoline, what's the acceleration? Well, the acceleration is actually upwards because he's moving down and slowing down. So there's a net force that's up. And what that means is that the force of the surface is more actually than the force of gravity. That's a great question. And then maybe Rohit, I've got you on top with your hand up. Did you have a question?
Yes, so if we have an alternative way of solving a question and we need to show the working for it, as long as a process of solving the question is correct, is that okay, or do we need to stick to the methods taught in lectures or in asynchronous content?
So that's a great question. It comes up kind of a lot. I would say, I mean, certainly the quiz on Tuesday is going to be multiple choice, so you can solve it any way you want as long as you get the right answer. That's the main thing. There's no showing work on this coming quiz, but I would like you to practice this whole 4-step method that's coming from the textbook, because I think that's going to be important in practicals, but and maybe on future quizzes. So, so it's a nice question. Okay. Moving right along. What do we got here? What time is it? 11:32. Okay, so we've kind of been alluding to this and skipping around, but someone was asking, I think Navid was asking, why is there more force from the surface than the force of gravity? And this has to do with the net force. So net force. Net force is sometimes written by this little sum. This is a sum of, is what that sigma. It's a capital Greek letter sigma. Means the sum of the force vectors is the net force. And it's not a new force being exerted. So example, here is a woman picking up a box. So there's a force of U on the system, I guess, the force of the earth on the system. So U would be this person pulling upwards. S would be the system. And they're not the same because there's a net force going up. So if you add these two forces, tip to tail, if she pulls upwards with 150 newtons, but the force of gravity downwards is 100 newtons, then 150 minus 100 means the net force is 50 newtons up. So, and you don't draw, this is the force diagram, you don't draw the net force on the force diagram, you kind of draw it beside it somewhere. And here's this experiment. So this is getting into Newton's second law. So she talks about this in the textbook quite a lot. Experiment 1 is a bowling ball rolls along on a very hard, smooth surface. What happens is that because of its own inertia, when you throw a bowling ball, it just keeps on going. So you can imagine once you throw that bowling ball, if it's halfway down the lane, the effect of your hand is gone. You're like, the only reason it's rolling is because it wants to keep rolling. So experiment 1 says that when the net force on the ball is 0, there's no external force, it just has a constant velocity, 0 acceleration. However, if you put a ruler and lightly push the bowling ball in the opposite direction of motion, with a constant force. And what you end up doing is that the velocity decreases with a constant acceleration. This little delta V is the same per unit of time if you're pushing it backwards with a constant force. And similarly, if you put the ruler behind it and try to push it forwards, again with a constant force, a constant maybe bend of the ruler, then it'll pick up velocity again with a constant acceleration. So experiments 2 and 3 imply that a constant net force produces a constant acceleration. And the velocity changes at a constant rate. That's what constant acceleration means. So we're getting into Newton's first two laws. Newton's first law says that for an observer in an inertial reference frame, when no other objects exert forces on a system, or when the forces exerted on the system all balance to zero, then the system continues moving at constant velocity, or if that velocity was zero, then it just continues to remain at rest. And for that, I've just tried to draw, imagine a cart that's just rolling along a track. There's very little friction. The upward and downward forces balance, and so it just goes along at constant velocity. So then you need a concept of mass. So mass is a scalar quantity that describes an object's inertia. It describes the amount of matter in an object. So mass is an intrinsic property of an object. So like there's some barbells that are listed in kilograms. It tells us something about the object regardless of where the object is, what it's doing, or whatever forces may be acting on it. So actually the mass is proportional to the number of neutrons and protons and electrons inside the object, right? And that doesn't change. So Newton's second law has this mass in it. It's actually an equation, which is that the acceleration of a system is equal to the net force divided by the mass. So it's proportional to the vector sum of all the forces being exerted on it. And it's inversely proportional to the mass of the system. So if you put a fan on, if you increase the force of the fan, then you'll increase, like double the force of the fan, you'll double the acceleration of the cart. If you add more mass to the cart somehow and keep the same fan, like if you double the mass of the cart, but keep the same force, then the acceleration will drop by a factor of 2. Okay, and those come from observations. Let's do a poll. 3 forces act on an object, F1, F2, and F3. In which direction does the object accelerate? So you're going to need to add these forces if you can. Tell me which direction you think the thing will accelerate away in. Oops. Okay, let's finish the polling. 3 seconds, 2, 1, 0. 90% of you have voted, which is great. Most of you chose D, so 82% of the ones who voted chose D. And what I think is that, oops. Yeah, I like D. And so the way you have to add these forces, there's various ways. This is actually showing what's called the parallelogram method. If you want to keep them all at the same, keep all the tails together, is you can draw a parallelogram of the 2 forces you want to add. So F1 plus F2 will actually be this diagonal where you form a parallelogram with F1 and F2. It goes from the tails up to the opposite side of that parallelogram. And then once you've got that, so this is F1 plus F2, then you can form another parallelogram to add that vector to F3. and then it goes along like that. So it's just another way of adding vectors. And what I think is going to happen is it's overbalanced in the down direction. It's definitely, there's only one force to the left. So it's going to be down and to the left. So it has to be D. And then the idea with Newton's second law is that the acceleration is a vector, the force is a vector, the mass is not a vector. So the acceleration direction is the same as the net force. Sorry, I should say net force. And it's just scaled by whatever the mass was. So very good. And then one more thing. So, and looking up here, oops. Looking at my chat window here. Some people are not seeing the poll. That's not good. Ah, chat window's gone to all attendees. Cutting you guys off. Yeah, the polls are meant to be for your learning. I don't know how to record it actually. Is the force of the Earth on these objects, gravity, is that the same as the weight? That's correct, yes. So I'm going to talk about that in a minute. Sorry for closing off the chat, but I think it's just a little distracting. I'm sure there's lots of places you can chat. Okay, big warning. Newton's laws, especially all of Newton's laws, only apply in an inertial reference frame. An inertial reference frame means that you're putting an XY axis, which is moving at a constant velocity, or it's staying still. So like the lab frame. If your reference frame is accelerating, then the Newton's laws don't apply. So here's another poll. First I'll think about it, then I'll launch it. So you are in a plane, which is accelerating. Now, remember planes? This is obviously a pre-COVID question. So imagine you're in a plane in the future, which is accelerating forward on a runway. And somebody has left a tennis ball in the aisle. You notice that the tennis ball is accelerating towards the back of the plane. You're kind of sitting there, you go, there it goes, rolling towards the back of the plane. So since it's accelerating, there must be a net force on it. F, acceleration is net force divided by m. So what's the source of the backward force on net force on this tennis ball? See if you can read through the list there and then also answer the poll. I'll give you another 20 seconds to read through these. Maybe I'll read through them just so that you... It's either A, air resistance pushing it backwards, B, the plane must be at an angle, so a component of gravity provides the net force that pushes the tennis ball backwards, C, the inertial force, D, the normal force, or E, Newton's second law is not valid in your reference frame. Okay, 5 seconds. And polling. So results were 49% of you answered E. And then the next most popular choice was C. Which is the inertial force. So in this course, we don't have a thing called the inertial force, but you've got the right idea. What we say in this course is that if you're in an accelerating reference frame and looking at that ball, then Newton's laws just don't work. You shouldn't be using Newton's laws. But I guess you could kind of think of an inertial force which would be pushing everything backwards. But the point is, what's really happening is that the tennis ball is just sitting there and you in your chair are accelerating towards the forward direction, right? So the tennis ball isn't even rolling backwards like in the inertial reference frame of the Earth. And then anonymous attendee said, sir, isn't the Earth always accelerating? So why can we use the frame as an inertial reference frame? Or can we? Or can we? So that's a great question. I guess the Earth is going in like in a circular orbit around the sun or something. So anyway, point is, the acceleration of the Earth is pretty small, and it's very constant. It doesn't change much. So we treat the Earth as if it's an inertial reference frame, and we neglect the fact that it's actually accelerating around the sun. And what really happens is that it just, if anything, it just affects how we define gravity's direction. So I do want you to treat the Earth and the lab frame, something that's not like the middle inside a car, as being an inertial reference frame. But great question. Okay, so once you're in an inertial reference frame, there's a bunch of forces. There's the gravitational force, and yet another question was, are we getting into 3.4 and 3.5? Yes. Again, I tend to get a little ahead of this book, but that gives us time for examples later. There's a normal force, there's tension, there's friction, both kinetic friction and static friction, which are both very different. We'll get into those. Springs can give a spring force. In Physics 132 in January, Professor Maple is going to start talking about electric force, magnetic force, and by that I mean Professor Sealfin. Thrust, like from a rocket, if you're expelling rocket exhaust in one direction, you get pushed along. Drag force, like there's air resistance or some fluid resistance. These are all forces. Also, I guess if you push something, muscle gives a force. And one of the things I'll show is this normal force. So let's start with normal force. And what I want to show, I'm going to stop the share, so there I am. And then, I know you're not going to like this, but what I want to do is change the microphone temporarily to be the webcam. Otherwise, I don't think you guys are going to hear me. So I apologize if there's a dog whistle kind of sound there. But what I want to show is that table over there. Right there. Okay, so here's a table. If I go and stand on it, there's also a little scale on it here. I can stand on the scale, and I can see the spring is going up to, oh dear, a little over 200 pounds. So what does that mean? What it means is that the spring is pushing upwards on me with a force that's equivalent to 200 pounds. So I think that's going to be some number of newtons, okay, which is not shown here, but I think it's almost about 900 newtons, yeah, something like that. So why is that? Well, that's because gravity is pulling down on me. And so the normal force, the upward force, adjusts itself to equal the gravity so that I don't accelerate. How does it do that? Well, it compresses the springs. So it knows that spring compresses until it reaches exactly to be the same magnitude as the gravity that's pulling me downward. So it's weird. You'd think there's nothing happening with me because I'm standing perfectly still. But all the time, there's a constant upward force, normal force pushing on me, and a downward gravity force pulling on me. Oh yeah, while we're up here, I wanted to do that tennis ball basketball experiment again. Let's try that. We're going to release them from rest, just in case you don't believe me. So the basketball is 10 times heavier than the tennis ball. Let's release from rest. They fall at the same rate. And so that's another thing. If you take the table out from under me, what will happen? I'll accelerate downward. Okay. So that's why you need normal force, and you all have an upward normal force on you, or else you wouldn't be, you'd be accelerating, you'd be in free fall. Back on my, so that's back on the microphone for my laptop. Let's go to class 6 again. Let's just share that screen. Okay. That's supposed to be me. Q&A is there. Chat and participants. Okay. All right. So continuing along. If I can find my pen. So you say the table exerts an upward normal force on Harlow. There's me water skiing in Idaho, actually on Payette Lake. There's a force of the rope on Harlow. That's called the tension force. We'll talk more about that. The rope exerts a tension force on Harlow. And here's gravity. So here's that angry bird. Somehow the Earth exerts a gravity force on the angry bird, which pulls it down. And there's an equation for that, which is that the force of gravity equals mass times g. Okay, where g is 9.8, also called the weight. So let's say you have a bird of mass 0.12 kilograms, and it's flying through the air. But his wings are tucked in due to anger or something like that. So let's just assume that air resistance is negligible. What is the acceleration of the bird? So let's draw a force diagram. What are the forces acting on the bird? Well, there's gravity downwards. F of the Earth on the bird is equal to the mass of the bird times g. And that's it. Only force. So the sum of all the forces acting on it is equal to mass of the bird times g. And then, so then you use Newton's second law to find the acceleration, which is what you're asked for. Acceleration equals the sum of the forces divided by the mass of the bird. So it equals the mass of the bird times g divided by the mass of the bird. And then what happens is that the mass of the bird cancels on the top and the bottom of the equation. So then you get the acceleration is equal to g in the downward direction. So now you kind of know what's going on with the basketball and the tennis ball. The force of gravity is greater on a more massive object, but it still accelerates with the same amount. And I can even do a thought experiment which might convince you that this is always going to be true. Imagine, let's do it down here. Imagine two bricks that are right side by side. Falling side by side. Okay, so we can draw them up here. Brick one, brick two. Now, they each have some mass, some force of gravity. If you connect the bricks by a very small strand of spider silk, then they will become one object because now they're connected. They're just one object. Connect them with spider silk. You would not expect greater acceleration. So we're running out of greater A acceleration. So if they're connected, now they're the whole object has twice the gravitational force on it as either brick did, but the whole thing's going to keep accelerating at the same rate because whether you connect it with the spider silk or whether you don't, the motion should still be the same. So it's not that surprising that these masses cancel. And this is just repeating. If an object of mass MO is near the surface of some large planet, which we call Earth, that has a radius of 6,370 kilometers, and if it has a mass of 5.97 times 10 to the 24 kilograms, then there will be a gravitational force acting on that object, often called its weight. So here's the object, I guess, O, which is towards the center of that planet. So you call that, by the way, the direction towards the center of your planet is what you call down. Going for time. Doing pretty well. Let me look quickly at chat. Yeah, so question is, so this is from Ariba, excellent question. So weightlessness is a result of no normal force. Exactly it, okay? So the reason you feel your weight, it's sort of weird. It's not because gravity is pulling you down. You feel your weight because the normal force is pushing you up. So like, for example, I mean, you could be weightless if there was no gravity, I guess, if you're way out in space or something, then there'd be no gravity acting on you, and there'd also be no normal force pushing you up, right? So you'd feel weightless. But you can also feel weightless if you're in an elevator, and then all of a sudden the elevator starts accelerating downwards at 9.8 meters per second squared. Then what that does is the normal force is no longer acting on you. There's only gravity pulling you downwards, and you'll feel weightless. So that's an excellent point. So let's talk a little bit more about elevators. Here's a poll. When I stand on a scale, that bathroom scale, it reads 185 pounds. Well, with my shoes, I guess it went up to about 200 somehow there. Anyway, 2.2 pounds is a pound is a unit of force. It was 2.2 pounds is equal to 9.8 newtons. So this means when you do the conversion that the upward force on my feet when I'm standing still is 185 times 9.8 divided by 2.2, it's 824 newtons. If I ride an elevator, which is accelerating upward at 1.5 meters per second squared, what is the upward force on my feet? So you might have questions on your quiz on Tuesday where you can guess the answer. And this is what I'm going to ask you to practice right now. I don't want you, I think we should solve this, but let's try to be lazy because you only have half an hour to do this 10 questions, and see if you can solve this question by just looking at all 5 of these answers and eliminating the ones that don't really make sense. A, 824, which is what I was measured when I wasn't accelerating. B, 950. C, 698. D, 0. Or E, negative 824. My feeling is that 4 of those you can just kind of eliminate with common sense. But then we'll also do it. In case those weren't the choices. Okay. We'll take a guess. I'll give you 5 seconds. 4, 3, 2, 1. 83% of you. So let's actually show. So a lot of people were voting for B. So what I'm thinking is that this was the same as at rest. And what's I think is going on is that if you're standing there, if I'm standing there on this scale, okay, and the whole elevator is going up, accelerating upwards, then there must be a net force is up. Okay, and so what is the force diagram on me? Well, it's pretty simple. It's just the normal force, F, I can call it F normal, and then the gravity force, F gravity. And you can sort of find the F gravity, it's just going to be this 824. So what I think, just from kind of thinking about it, is that F normal must be greater than F gravity, okay, to give upward unbalanced force, upward net force. Does that make sense? It can't be the same or else you wouldn't be accelerating. So that one can't be right. It also can't be less. If the upward force on my feet was less than the downward force of gravity, which is 824, then I would accelerate downwards. It can't be 0, that's sort of weightlessness. And it can't be negative. Maybe this normal force can't pull. Maybe if there was glue on my feet or something like that, pull downwards. So it can't be that. So the only thing left is B. And indeed, if you work it out, I guess F normal minus mg is equal to m times a. You have to figure out the m somehow in here. I would say that m is equal to this fg divided by g. So it's actually 84 kilograms. So you have to figure that out. So then you can do F normal is equal to m times g plus a equals 84 kilograms times 9.8 plus 1.5. And that's how I got the 950 newtons. Say normal. Okay. 84 kilograms I had to figure out from the fact that when I was standing still, the upward force was 824. So that's when the force is balanced with the force of gravity. So I know that that is equal to m times g equals 824. I can solve that out for mass by dividing by g. So 824 divided by 9.8 gave me the 84 kilograms. That's a good question. Okay, guys. Before class 7 on Friday, I would want you to think about the following reasoning. There's a mistake in this reasoning. When you pull a wagon, Newton's third law states that the wagon pulls back on you with an equal and opposite force. These forces should cancel, so it's impossible to pull a wagon. Okay, so that's not true. So where's the flaw in the reasoning? So thank you very much. I'm going to turn off the recording and see if there's any questions. Where am I here?